That's section 2, which is solving linear systems with real eigenvalues, and then section 6.3 will be solving them with complex eigenvalues. But first, let's look at the second order homogeneous differential equation, and let's solve it. We're going to start with the characteristic polynomial, and we're going to factor that, and that'll factor into r minus 3 and r minus 2. So it looks like our roots are, I don't know why it's doing that, our roots are 3 and 2. So we can build the solution by doing a linear combination, c1e to the root 1t plus c2e to the root 2t. So there is our solution, and this is what our characteristic polynomial looked like. Now we're going to take that second order differential equation and we're going to convert it to a first order system in this matrix vector form where the derivative equals this matrix times the variables. And then we're going to find the eigenvalues and eigenvectors for A and kind of compare them here. So to convert, we're going to start with x1 is going to equal y, which means x1 prime is y prime, but we're also going to call that x2. And so then we have x2 prime will equal y double prime. So we want a system of equations that has x1 prime equaling something and x2 prime equaling something. Well, the x1 prime is y prime, which is x2. So we can put x2 right here. That will always be the case when you're doing a system conversion. But now the x2 prime depends on what the differential equation was. So let's go ahead and do the substitution. Y double prime is x2 prime minus 5y prime is x2 plus 6y, that was x1, equals 0. Now we can take this equation and we can solve it for x2 prime. And then we can put the solution here, and we want x1 first, so we'll move the 6x1 over and be negative 6x1 and then plus 5x2. So this is our system of equations that correspond to this second order differential equation. Now let's find the eigenvalues and eigenvectors. So first of all, we want to take the determinant of a minus lambda I. Well, let's write down what a would be then. And we just pick off coefficients. We have the x2 here. We have no x1s. We're going to put that first though. So there's 0, and then x2 is 1. And in the second equation, we got negative 6 on the x1s and 5 on the x2s. So there's our a. Now we're going to take a minus lambda I, so we're going to subtract lambdas down the main diagonal. This is how we find eigenvalues and take the determinant of that matrix. So negative lambda squared, negative lambda times negative lambda is lambda squared. Then I've got minus 5 lambda, and then multiplying up I have minus and minus 6, which makes a plus 6 equals 0. Now remember our characteristic polynomial was r squared minus 5r plus 6 equals 0. No coincidence that these guys have the same solutions. So we could factor it just like we'd factored previously for the r's. We're factoring with the lambdas here, and it would be negative 3 and negative 2. So our eigenvalues, there's one of them is 3 and the second one is 2. Now to find corresponding eigenvectors, we need to take the eigenvalue and put it in the a minus lambda I. So let's start with the eigenvalue of 3. We're going to put it in this a minus lambda I, but not as a determinant this time. So if I put in 3, I have minus 3, 1, minus 6, I'm putting in 3, 5 minus 3 is 2. You can see the dependency here. If I did negative 2 row 1 and added it to row 2, it would zero out row 2. So we don't really need to do the row operations on 2 by 2s. We can just put the variables back in. Negative 3x1 minus x2 equals 0. So negative 3x1 equals x2. So for my eigenvector, I need to choose an x2. I'll pick -3. So when I put that in here, -3 equals -3x1. Those would cancel and x1 would be 1. So there's my eigenvector, kind of all over the screen here. So I'm going to back up to find the second eigenvector. That would be for the eigenvalue of 2. So if I go to my A minus lambda I matrix and I put in a 2, I have -2, 1, -6, and 3. We can see that dependency there. Put the variables back in, and -2x1 plus x2 equals 0. So 2x1 equals x2. So for the second eigenvector, we would let x2 be 2 and x1 would be 1. So we have found our corresponding eigenvectors here that correspond with these eigenvalues. Now, when we just had not a system but just a differential equation, we found that the solution was e to the rt. And so we would think maybe we'd want to try a similar thing. If we were trying to figure out what might solve this system, we would try e to the lambda t, because we saw lambda and r ended up being the same in our system that we converted to, in our DE that we converted to a system. So it might make sense to try E lambda t, but we need it to have, if it's two components, we need to have two components. So what if we times it by the eigenvector? So what we want to do is see if that would solve the differential equation. So let's go ahead and try that. And when we try that, let's see if it really is a solution. So this was our matrix A, and we did find we'd converted that, and we did find the eigenvalues. They were 3 with the corresponding eigenvector of 1, 3, and the other one was 2 with the corresponding eigenvector of 1, 2. So what if we tried taking e to the eigenvalue t multiplied by the eigenvector? Let's see if that's a solution. Let's distribute that through. That would be e to the 3t and 3e to the 3t. What if we took that? I don't understand why that pen's being funny. What if we took that and put it right here and see if it's a solution? So for the x, we're putting in e to the 3t and 3e to the 3t. So let's go ahead and multiply these. We go across the row and down the column. We have 0 and we have 3e to the 3t. So 3e to the 3t. Let's do second row down the column. We have -6e to the 3t plus 15e to the 3t. That's 9e to the 3t. Now, does that equal the derivative? So let's take this matrix and just take a derivative. The derivative of e to the 3t is 3e to the 3t, and the derivative of 3e to the 3t is 9e to the 3t. So hey, that is a solution. That works. Let's try e to the second eigenvalue t times the second eigenvector. And so that would be e to the 2t and 2e to the 2t. And so if we went back up here and we tried that for our x, this would be e to the 2t and 2e to the 2t. And when we do the multiplication, let me just get room to do that. Cross throwing down the column, 0 and e to the 2t. And then across the second row, -6e to the 2t plus 10e to the 2t is 4e to the 2t. Let's take this now and take a derivative and see if it's equal. E to the 2t's derivative is e to the 2t. Chain rule generates a 2 out in front. The second one, 2e to the 2t. Derivatives e to the 2t with another 2 from the chain rule, it'll make that a 4, and yes, it does work. So the way we're going to find solutions to systems is we are going to take e to the eigenvalue times the eigenvector, and we have two different solutions that work, and so we could build all solutions with those if we put those in a linear combination. So that's what we want to do to solve this system. So the solution is going to be C1 e to the 3t multiplied by 1, 3 plus C2 e to the 2t multiplied by 1, 2. So that's my general solution. Now keep in mind what these stand for. This was x1, the top ones, and x2 are the bottom ones. So x1 is C1 e to the 3t plus C2 e to the 2t. That 3 didn't show up there. Okay, so x2 is, we do the lower ones, the second component, so that's going to be 3c1 e to the 3t plus 2c2 e to the 2t. So there are our solutions. This is a way to write it using the vectors, or you could just look at the first components and get our x1 and look at the second components and get our x2. So in general, and I've kind of got these, I didn't plan the slide to where I was going to write, so let me just erase this so it's out of the way. Our general solution is going to be then a linear combination of e to the eigenvalue t eigenvector for each of the eigenvalues and eigenvectors. So now let's see some examples. So the first thing we're going to do to solve this system is take a minus lambda I, which is subtract lambdas down the main diagonal, and find the determinant of that. So minus lambda times minus lambda is lambda squared. Minus 3 lambda minus 2 lambda is minus 5 lambda. 2 times 3 is 6. Minus 2 is 4 equals 0. So we are going to factor that. We have lambda, and minus 4, minus 1. So eigenvalue 1 is 4, and eigenvalue 2 is 1. Let's go ahead and take that first eigenvalue then of 4, and we put in our matrix A minus lambda I. 2 minus 4 is minus 2. Then we have a 2 and a 1, and 3 minus 4 is minus 1. So you can see the dependency here, and so let's put the variables back in. We know one of the rows would cancel the other one out. I'm going to put the variables back in for this row because they're multiples of each other, and this one's smaller, easier to work with. So we want vectors, so the first component of the vector minus the second one is going to equal 0. That's what we get when we put those variables back in. So v1 needs to equal v2. So our first eigenvector is going to be, we'll just put a 1 in there. So we've got 1 and 1. Okay, pen's acting up. I don't know what to do about that. All right, so let's go ahead and take the second eigenvalue, which was 1. Put it up here in our a minus lambda I. 2 minus 1 is 1. Then we got 2. Then we got 1. 3 minus 1 is 2. You can definitely see the dependency there. Let's put the variables back in. v1 plus 2 v2 will equal 0. So v1 is minus 2 v2. So let's just pick something that works there. We can pick anything, but we're after an easy one. What if we put in a negative 1 for v2? That means v1 would be 2. You could, any of these, as long as they're scalar multiples of the other, is going to work. All right, so we will build then our solutions by taking e to the first eigenvalue t times the first eigenvector. The second building block for our solution would be e to the second eigenvalue eigenvector. So if we put those in a linear combination, then we will have our complete solution. This would be our answer. We could break it down in components. X1 would be the upper parts, using the upper parts of the vector, and x2 would be using the lower parts of that vector. Now I wanted to show you a graph of the solutions, but it's going to go over the top. I should have had these moved over, forgot that was going to show up. So I've got to erase these here so we'll be able to see this graph. But you can plot, I'm going to do it over here, we can plot the eigenvectors. So this first one is 1, 1. If I go over 1 and up 1 and I do scalar multiples of that vector, it would look like a line like that. And the second one would be 2 and -1, so it would go like this. Where the eigenvectors intersect is an equilibrium, so there's an equilibrium solution here at 0, 0. But it turns out, because this e to the 4t, what does e to the 4t do as t goes to infinity? It goes to infinity. And so this is going to head away on the eigenvector, and if this C1 would have been a negative, then it would have been negative and it would be going larger in the negative direction. Now the second eigenvalue and solution here that corresponds with the second vector is an e to the t, which also goes to infinity. So solutions are going to be heading away from the origin because these eigenvalues are positive, and e to the positive t is going to blow up, go to infinity or negative infinity. This is what it officially looks like plotted. The equilibrium is unstable because things are heading away from it, and these are a couple, 2 or 3, 4 representative solution curves of how a solution might kind of try and move along one vector but then head towards infinity. This one corresponded to e to the 4t, so they ultimately want to go in the same direction as e to the 4t because it will dominate over e to the t. Okay, let's look at another example, and in this particular example we also have an initial value. So the first thing we're going to do is we are going to find a minus lambda I, so minus 2 minus lambda, 1, 1, and minus 2 minus lambda. And now let's go ahead and, just trying to fix this, minus 2 minus lambda. Find out when that determinant equals 0. This is going to be lambda squared. Then we have 2 lambda, another 2 lambda, so plus 4 lambda. And then we have 4 minus 1, which is 3, equals 0. So this will factor, and we will have lambda and lambda plus 3 and plus 1. So eigenvalue 1 is -3, eigenvalue 2 is -1. Doesn't matter which order these are in. All right, so let's go ahead and start with eigenvalue 1 of 3. And let's find a minus lambda I, so we're putting a 3 in. So -2, oh, it's a -3, so we got -2 minus, and minus makes a plus, so that will become a 1, and then 1, and then 1, and of course the other one's still going to be a 1 as well. We can definitely see the dependency there. So V1 plus V2 equals 0. And so we have V1 equal -V2. So our first eigenvector, let's let V2 be -1, and that means V1 is 1. The second eigenvalue is going to be -1. So when we put that in, and the minus and minus makes a plus, so -1, -2 plus 1 is -1. Then we have 1, 1, and -1. So let's go ahead and put variables back in. -V1 plus V2 equals 0. So V1 equals V2. So our second eigenvector, let's let V2 be 1. That means V1 is also a 1. So then we can build our complete solution with the building blocks of e to the eigenvalue t multiplied by eigenvector. And the other one is e to the eigenvalue t multiplied by that eigenvector. If we put those together in a linear combination, then this would be our solution to this system of differential equations. Now if we plotted those eigenvectors, 1, 1 over 1 up 1 here, and then scalar multiples, this time though it's e to the negative t. You think of what e to the negative t does. As t goes to infinity, it goes to 0. So these guys, boy, that's crooked, isn't it? Anyway, these guys are going to go towards 0. Plotting the second eigenvector, 1 and negative 1, there's an equilibrium solution at the origin. This is also a negative, and so these guys are going to head towards the origin as well. So this is going to be a stable equilibrium, and solution curves would kind of curve and flow in to the origin. Now the thing that we didn't yet do was take our initial value and find the exact solution curve, and so we need to do that. And so what we're going to do is we are going to, for t, put in 0. So if I'm looking at my solutions, if I put in 0, what I'm figuring this out is at 0. If I put in 0 here, these will be 1, so they'll be gone. So let's write down what we have and what it needs to equal. So let's do the upper components first. So I'm going to have C1, looking at the upper ones, that's here, like this, and then I'm going to have plus C2, and that needs to equal whatever my initial value is for the first component, and that's 3. Now looking at the lower components, the second components, I have C1 minus C2, and that one needs to equal 1. So we can solve this system of equations. 2c1, I'm just adding them together. 2c1, the c2's cancel, equals 4. So c1 equals 2. So I found this first constant right here. That's going to be a 2. And then if I put 2 in for c1, and then I have plus c2, that needs to equal 3, so C2 must be 1. So this would need to be a 1. So my solution then is 2 in here and 1 in there. And this is what the graph looks like with the flow of some of the solution curves, how they kind of curve around but end up heading towards 0. The specific one that has the initial value of 3, 1 is here in black. All right, let's look at another example. This time again we're going to do a minus lambda I, 1, 4, 1 minus lambda, which puts negative lambdas down the main diagonal. And then if we multiply, that's going to be lambda squared minus 1 lambda, another minus 1, which is minus 2 lambda, and then 1 minus 4, which is minus 3. So if we factor that, that will be lambda, lambda, minus 3 plus 1. So one of our eigenvalues is 3, and the other one is negative 1. Let's go ahead and find corresponding eigenvectors. So for the eigenvalue of 3, our a minus lambda I looks like negative 2. We're just putting a 3 in here. 1, 4, and negative 2. So we have negative 2 v1 plus v2 equals 0. So v2 equals 2 v1. So corresponding eigenvector, let's put in 2 for v2, and that would make v2 1. If there was a 2 here, equals 2 v1. v1 is 1. Now let's take the second eigenvalue of negative 1, and we have 1 minus a minus 1, which makes a plus, so that's going to be 2, 1, 4, and 2. Putting the variables back in, 2v1 plus v2 equals 0. So 2v1 equals negative v2. So second eigenvector, typically plan it so the first component's positive, but it really doesn't matter if you got a scalar multiple. So I'm going to put in negative 2 here, so that will make that 2, so v1 will be 1. Alright, so I'm going to build my complete solution here by putting those in a linear combination. And then if we looked at what's going on with the eigenvectors, so let's go ahead and make a quick sketch. The first one is 1, 2, and we put it like this, and that corresponds with a positive eigenvalue, so I'm going to make the arrows going out. The second one is 1, negative 2, so something like this, and that eigenvalue is negative, so that one wants to go in. So what's going to happen when we look at the curves, they're going to want to try and head in some, but then that positive is going to make them go out. Here is a graph of the phase portrait. The equilibrium solution at the origin is still unstable, because even though this one makes it want to head towards the origin, this one is going to ultimately dominate, and the solutions will go to infinity or negative infinity. Okay, let's see what happens with a repeated eigenvalue. In this particular case, we have a minus lambda I is 3 minus lambda, 0, 0, and 3 minus lambda. And so we have lambda squared minus 3 lambda, and minus 3 lambda is minus 6 lambda, and then 3 times 3 plus 9 equals 0. So this will factor into lambda minus 3 twice. So we have just one eigenvalue this time. It's a repeated eigenvalue of 3. So let's see what happens when we try and find an eigenvector. So our lambda is 3. Put that in. 3 minus 3 is 0, 0, 0, 0. What does that mean? That means that anything will work, because both v1 and v2 are free to be anything. So any vectors will work. We need two linearly independent eigenvectors. So the first one I'm going to pick is 1, 0, just because that's simple to work with. And the second one, to get something that's independent, how about 0, 1? So I'm going to put them in a linear combination then, and we will have this. As far as the phase portrait and looking at the eigenvectors, then because it's a positive eigenvalue, we would make those going out, and it turns out that the solutions end up being linear going out. We still have an unstable equilibrium solution at the origin, and the solution curves would just be linear heading out. All right, now another thing that can happen with a repeated, and we're going to see right here. So let's go ahead and do our a minus lambda I, 4, 6 minus lambda. And lambda, negative lambda times negative lambda is lambda squared. Negative 6 lambda minus 2 lambda is negative 8 lambda. And then we have 12 minus a minus 4 makes a plus 4, which is 16 equals 0. So that will factor, and it's going to be a repeated factor. It'll factor into lambda minus 4 twice. So our eigenvalue is 4. Let's go ahead and put that in to find eigenvectors. If we put a 4 in, we have negative 2, negative 1, 4, 6 minus 4 is 2. You can see our dependency there. We have negative 2v1 minus v2 equals 0. So negative v2 equals 2v1. So eigenvector going to be, let's put negative 2 in for v2, which will then make v1 1. Okay, so we have our eigenvector, but I only have one this time. I don't have a way to get a second one that goes with that, like this. So what do we think about when we have a repeated root? if we're trying to figure out what might be good to try, one of our solutions would be e to the 4t times the eigenvector. I'm just going to put times the eigenvector. So it would likely make sense to try t e to the 4t times the eigenvector. So let's try that. Let's actually put that in and see what happens. We need this to solve, and I'm just going to write this as our x prime. I'm just going to call that a for just checking it out. All right, so let's sub it in here and see if it works. So I need its derivative. This is a product. So I've got first times the derivative of the second plus the second times the derivative of the first, and then remember v is just a vector of constants, so we can just stick that on the end. We want to know, does that equal if we did a times that solution, t e to the 4t v? Well, there's a problem here, and the problem is for these to both be equal, you'd equate coefficients, and we have t e to the 4t terms that we could do that, but this piece right here showed up in the derivative, and I don't have anything for it over here. So that guess is not going to work. I need an extra term that has e to the 4t as part of the solution. So what we're going to do is we're going to figure out what we would need to do to find that. So what we're going to do to try and find a second solution to this is we're thinking that we need some t e to the 4t times the eigenvector, but then we need some e to the 4t times some other vector. We're going to call that other vector u. All right, so let's take the derivative. First times the derivative of the second plus second times the derivative of the first. And then our second term, we just need a chain rule for that one. So it's 4e to the 4t u. So that is what our derivative side looks like. And we want to put that equal to, I'm going to write it down below because I need more room. So I'm going to have 4t e to the 4t eigenvector plus e to the 4t eigenvector plus some 4e to the 4t with some other vector so that it will solve it, and we need to know when that equals a, and our solution then was t e to the 4t eigenvector plus e to the 4t times some other vector that we're trying to find. And now let's equate coefficients. So looking at our t e to the 4t terms, got t e to the 4t, it looks like I have 4 times the eigenvector. That would have to equal a times the eigenvector. I would have av minus 4iv equals 0. And if we factored the v out, we would have a minus 4i v equals 0, and that is just, we already know that that's true because that's exactly what we did, was the a minus lambda I to find this. So the first condition is just going to be there and going to hold, so we're good with that. So let's go ahead and look at the other part and the coefficients. Let me do a different color. Let's do the coefficients on the e to the 4t's, and what do I have? It looks like I have a v plus a 4u, and that needs to equal a u. All right, so let's go ahead and get the u stuff on the same side. So I have a u minus 4, and I'm going to go ahead and put the I in there, u, so I can factor that out, equals v. So bottom line, when I factor that u out, I have a minus 4 I, which is like our lambda I, u equals v. So what all of this tells me is that to get the first eigenvector, that's fine, just like I found it, but to get the u, I need to figure out a minus lambda I augmented with that eigenvector, that first one I found, in this case the one, -2, and that will give me the u. It's not an eigenvector. They actually call it a generalized eigenvector. It's not a true eigenvector, but it will work in building the solution. So what we found, and let's go ahead and do it then. I'm going to do it on the next slide. Let's put the information in that we have, and then we will be able to find the u. Okay, we knew that the eigenvalue was 4. The eigenvector we already found, and it was 1, -2. Now what we're interested in doing is finding this u so that we can build the solution. And so we are going to take the a minus lambda I, so that was 2 minus 4, which was -2, -1, 4, and 6 minus 4 is 2. And we're going to augment that with the eigenvector. Instead of putting 0, 0 here, we're putting the eigenvector, and we're going to solve that, and then we need, for the u, there'll be scalar multiples, and we'll pick an easy one to work with. So let's go ahead and do that. I'm going to do row operations. So I'm going to do -1/2 row 1, and that'll make that a 1 and a 1/2 and a -1/2. And then I'm also going to do, I'm going to just use this original row 1 over there, and I'm going to do 2 row 1 plus row 2, and I should see the dependency. -2 times 2 is 4, added to 4 is 0. -2 to 2, you can see that that would zero that out. So let's put our variables back in. We'd have u1 plus 1/2 u2. Let's go ahead and equals, move that over, 1/2. Let's clear to fractions. 2u1 plus u2 equals 1. So let's let u1 be k. So just some constant. I'm not using t because we're going to use that in building our solution. So we'd have 2k plus u2 equals 1. So u2 equals -2k plus 1. So if we express this as vectors here, we've got a k, and then we have one that just has a constant. So we'd have 1 and -2. That's the piece that goes with our eigenvector. And then what we have on the other part of it is 0 and 1. So now we're ready to build the general solution to this. First it's going to be c1 e to the eigenvector t multiplied by eigenvalue. And then our other piece is going to need two parts. The first part is going to be t e to the eigenvalue eigenvector, and then we need our second piece on there that corresponds with our u, and so that one is going to be e to the 4t multiplied by what we found that u was. So what we did here is we found what's called a generalized eigenvector, our u, to put on the solution needs to have the t e to the eigenvalue t eigenvector, but then it also needs that additional piece. So this is the solution, but I had a typo there. It should be a +1. Okay, so this is what it looks like. I'll get this out of the way here. We only have one eigenvector, so there's only one drawn here, and the arrows head away because the eigenvalue is positive, and the solution curves look something like this. So if you need to solve a system with insufficient eigenvectors, and that would come from a repeated root, if we're looking at a 2 by 2, this was the process we go through. We first find the eigenvector, and then we find an additional vector u by taking the a minus lambda I, and we want to figure it out when times this u it equals the eigenvectors. So we took a minus lambda I, we augment it with v, and we find the u. Then our complete solution would be built by taking C1 times the eigenvector, eigenvalue t eigenvector, and then C2t e to the eigenvalue t eigenvector plus another additional piece of C2 e to the eigenvalue t with the u that we found. Often when they write the solutions, they factor out the C2 and the e to the lambda t, so they just have TV plus u there. Remember, that's called a generalized eigenvector. All right, now we need to look at a couple of ways we can use systems of equations to model different situations. So the first one that we're going to look at is the tanks. We did a mixing problem with a tank before, had something stirred in the tank, but now we can have an interaction of tanks. Remember when we did the tank problem, we figured out the rate of change of the whatever's in the tank. In this case, this is salt. The rate of change of the quantity of salt was rate in concentration in minus rate out concentration out. So that's what we did when we had a single tank. Well, we're going to do the same type of thing. We have two tanks. So the first tank we have is our x1 of t tank. Okay, so if we want to know the rate of change of the amount of salt in the first tank, we're going to set that up. Let's actually write down a few other things that we have here. Each tank holds 100 gallons, so I'm just going to note that on the tank so that I can remember that when I need it. And there's 10 pounds of salt dissolved, so that's giving me my initial condition. At time 0, tank 1 quantity of salt is 10, and tank 2's quantity of salt is 10. This is in pounds. Okay, fresh water flows into tank 1, so the concentration in for tank 1 is 0 and at a rate of 3 gallons per minute. So this one coming in, you'd take rate in, concentration in, and the well-stirred mixture flows into tank 2 at this rate. It's given there, and then tank 2 is pumped back into tank 1, and then there's some going out. Okay, so rate in, concentration in, but there's another going in. Got to add that one on. Rate in is 2 gallons per minute. Concentration in would be whatever the concentration is in tank 2, and the way you get concentration is you take the amount per volume. So the amount of salt in tank 2 divided by the volume of tank 2. So there's two different terms for rate in, concentration in, because there's two different things going in. Now we subtract off what's going out. That would be this bottom one. So that would be 5 for the rate out, and the concentration out would be whatever the concentration is in tank 1, which would be the amount of salt in tank 1 divided by its volume. So now let's do the same thing for tank 2. If we look at what's coming into tank 2, the only thing coming into tank 2 was whatever's going out of tank 1. So it was 5 for the rate in, and the concentration in would be the concentration of what's coming out of tank 1, so what's in tank 1. Now we have two different terms going out, so those will both be minus. First one, the rate out is 2 gallons per minute, and the concentration would be x2 over 100. And then for this second piece, we have another minus term. Rate out is 3 gallons per minute. Concentration out is x2 over 100. So there's our initial value problem. Let's write these equations just a little simpler. x1 prime equal 3 times 0 is gone. I'm going to write these as decimals. 0.02, and let's actually write them in the order. We're going to put x1 first. So negative 0.05 x1 plus 0.02 x2. So there's our first equation. Our second equation, we have 0.05 x1. These are like terms, so I can combine them and get minus 0.05 x2. So these, along with our initial values, are the model for our tank problem. It's very involved to solve, and so I would likely have you just set them up because you've just got a lot involved to do the solution, and it's not something you'd be able to do on a test. I actually took these differential equations, wrote it in matrix vector form with my initial values there, and I went to technology and asked it to find the eigenvalues, and notice it finds the eigenvalues, and it also they're kind of crazy looking, and it also finds the eigenvectors. So you could build the solutions with these, and I did that here. As ugly as that looks, that would be the solution. And then I could find the C1, C2s by putting 0 in here, but that still got me some ugly stuff equaling 10 and some other ugly stuff equaling 10. And so I actually the second one's not ugly stuff. It's pretty easy. So I just asked technology, these are Wolfram Alpha, to solve these two equations together, and it gave me what I needed to have on the front of there for the complete solution. This is my C1 and C2. So real life can be ugly as far as numbers go, but with the help of technology, very doable if you understand how to set up the model. This is just a graph then of what was going on in each of the tanks. We got one more model to look at. We're going to look at an electrical circuit, but now we can look at a more complex one that can have more than one loop, and because we can do a system. And the two things we're going to use are Kerkoff's first law that says current flows into junctions must equal current flows going out, and then Kerkoff's second law, the voltage drops around a loop must equal 0. They've all got to cancel each other out essentially. So let's look right here first. This is a junction. The current is splitting there, so I1, current 1, equals I2 plus I3. So that's the first connection we have using Kerkoff's first law. Now, other than that, let's go ahead and use the second law and look at the voltage drops, and we're going to look at them around each loop. So first we're going to go around loop 1. And so we have this inductor, and if we remember, the voltage drop across an inductor is the inductance times the rate of change of the current. That's current 1 going through that, so we need its derivative. Okay, then as we go around the loop, we go through this resistor, and that would be the resistance times the current, and that current is I3 going down there. And then as we go around the loop, we've got another resistor, so that's going to be resistor 2, and the current going through that is now going to be I1, because we've joined those back up again, and that would equal our voltage here. Now, in order to use it in a system, we would want to divide everything by L1 so that we could solve for the derivative there and have it by itself. So these would just put L1s, we just usually do them over the constants like that. All right, let's do the second loop. So the second loop, going around just this loop, the first thing we see is that inductor, so that's going to be L2, and the current through there is going to be I2, and we need the derivative of that. The voltage drop is the inductance times the rate of change of the current. Now, if we went around this loop, because we're actually going in the opposite direction of the current flow, we put a negative on that. So that would be resistor 1 and current I3, and that would equal 0 because we don't have any voltage there. Now, if there was no voltage applied to this at all, then this one would also be 0. So now as we look to express this as a system in kind of a nice, neat form so we could find eigenvalues and eigenvectors and solve, first thing is I've got 3 i's, I1, 2, and 3, and I've only got 2 variables here, I1 prime and I2 prime. So I'm going to solve this for I3. That's going to be I1 minus I2, so that I don't need I3 in these equations. And so I'm going to replace this with I1 minus I2, this I3 right there. and I1 minus I2 right there as well. All right, let's write down our system of equations in standard form then. We have I1 prime will equal, so there's going to be minus R1 over L1 I1, and then we've got minus R1 over L1 I2, and then we have minus R1 over L1 I1, and then plus V. Now I2 prime is going to be just moving those over. This was a minus already, so it's going to be a plus R1 over L2 I1, and then this minus and this minus make this a plus, so when we move it over it's going to be a minus R1 over L2 I2. So this is our system of equations. If we had numbers for resistors and inductors, it wouldn't look quite so scary. I kind of did it in its general form here of what I got, kind of combining things and how it would look like in its matrix vector form. Keep in mind, if you had the values for those, these would all just be numbers in here and in here.